Hey guys, welcome back to my YouTube channel. In today's video, I'm going to be going over cyclohexane stability, and I have some practice problems that we're going to be doing. So to start off, we have cyclohexanes in the chair conformation with different substituents attached. And so essentially the main idea you want to have in your head is that the equatorial position is more stable than the axial position. And so in all of these, we're going to analyze those positions and see which ones have more axial positions and which have equatorial positions to see which ones are more stable. So in this first molecule, actually all these molecules, we have a tertiary butyl on an equatorial position. So as you can see here, oops, that arrow is not pointing to. So right here, right, we have a tertiary butyl in an equatorial position. And how do I know it's equatorial? So if you look at the carbon it's attached to, the vertex is going down. And the tertiary butyl is pointing up. If it was on an axial position, it would match the vertex, but it doesn't, so it's equatorial. So in this problem, the tertiary butyl is of no significance because it's on the equatorial position in all of them. So essentially we're comparing the methyl groups. So in this first one, if we look at the vertex here, it's a vertex up, but the methyl group is going down, so I know it's equatorial. And this vertex is going up, the carbon vertex, and the methyl is going up. And so I know that methyl is on an axial position if it matches the vertex. So here I have two equatorials and one axial. And yeah, so second molecule, I have two methyl groups facing, so this first one is facing down, this one is facing up. Because they're opposite to the vertexes, they're both equatorial. So here I have three equatorials. And my two equatorials, they're in opposite directions. Next molecule, I actually have the same thing, right? So this methyl group right here, it's opposite to its vertex, so it's equatorial. Excuse me. And then this methyl here, it's also opposite to its vertex, so it's equatorial. So three equatorials. Next molecule, I have two methyl groups that are facing in direction with their vertexes. And so I have two axial methyls, which is a big no-no in stability because of diaxial interactions. So here I have one equatorial, but then I have two axials in the same direction. They're both up. And in this last molecule, I also have two axial methyls. And they're actually in opposite directions. Okay, so what's the most stable molecule? So if we look at our molecules here, one second. Sorry. If we look at our molecules here, the one with the three equatorials will be the most stable, because equatorial positions in general are more stable than the axial positions. And we only have two molecules with, or two cyclohexanes with three equatorials. And actually, in this first one here, the two methyl groups are in opposite directions. But in this one, they're both in the same direction. So this methyl group on the left here, that I circled here, it's down. This methyl group here is also down. So they're both down. And as you can imagine, there would probably be more steric hindrance between the two because they're both in the same direction. Therefore, since this molecule here on the left of it, they're in opposite directions, the methyl groups, there's going to be less steric hindrance. So I'm going to assign this the number 1 ranking in terms of stability. Then this as number 2. And then if we look at our axials, this cyclohexane only has one axial, so I'm going to give that the 3. Then these two over here have two axials, two axial metals. And this one on the very right has the two axial metals in opposite directions, so it's less steric hindrance. So I'm going to give this the 4. And then this one will get the 5 because it has two axial metals in the same direction. So lots of steric hindrance. And yeah, so that's our first example there. So second example, I have a cyclohexane with some substituents. I see a tertiary butyl. I see stereochemistry. Sorry. I am coughing a lot. So when you see these type of problems, you want to number the ring in such a way that you have your biggest group on an equatorial position. You never want to have a tertiary butyl on an axial position. That's another big no-no. If you have a tertiary butyl on an axial position, something bad will happen. I've never tried to put a tertiary butyl on an axial position, so just stay away from that. It's just way too big. So if I were to number this, you can number it in any way you want, in any direction, but you need to make sure you're numbering your chair conformation in the same direction. So I'm going to number it this way. I'm going to give my tertiary butyl the number 1 so I can, it's just easier for me. So I'm going counterclockwise, or I'm going clockwise actually. 1, 2, 3, 4, 5, 6. And then I'm going to draw my chair out. It's not the best looking chair. And if it's on a dash, which all of these are, it's going to be down. So this is down, that's down. And so if I have my 1 here, my 2 there, 3, 4, 5, 6, my 1, the vertex is pointing up, and then my tertiary butyl is on the down position, so it's going to be an equatorial tertiary butyl, which is what I wanted. And so at 3, I have a down methyl group. This is another equatorial. And then at 5, I have another down methyl. So actually, this first molecule, I have 3 equatorials. Cool. Second cyclohexane, I have a down tertiary butyl. And this methyl here is on a wedge, so it's up. And then I have another down methyl. So 1, 2, 3, 4, 5, 6. Draw my chair out. Oh, that is not a good looking chair. Anyways, tertiary butyl will still be down, so it will be on the equatorial position. 1, 2, 3. And then my methyl is going up this time, so it's facing in direction with the vertex. See this vertex here? It's going up. So if I put up my methyl up, that will actually be an axial methyl. And then my 5th methyl, which is, so this is 1, 2, 3, 4, 5, 6. It's going down, so that's going to be an equatorial. So here I have 1 axial methyl. Down, up, up. And then I draw my chair out. Number it. Tertiary butyl is on down. And then at 3, I have an axial methyl once again. And then at 5, I have an up methyl. It's actually axial again. So here I have, 1 second. Okay. Sorry. So here I have 2 axial methyls. And yeah. So this is actually 1 axial methyl, 2 equatorials, 1 equatorial. And so this next chair, or next cyclohexane, I have a down, up, down, then number it. One, two, three, 4, 5, 6. At 1, I have my equatorial tertiary butyl. At 3, I now have an axial ethyl. And then at 5, I have a down methyl. So I have 2 equatorials, but I have an axial ethyl. Last molecule, down, up, down. 1, 2, 3, 4, 5, 6. Draw my chairs out. Right, so I have my equatorial tertiary butyl, and then at 3 I have an axial isopropyl, so that's not looking too good. And then 5 I have an equatorial methyl. So I have one axial and 2 equatorial. Okay, so we have all of our chairs, and now we can analyze. So the one with the all equatorials will be the most stable, so that's 1. And then there's only one cyclohexane with 2 axials. Sorry. I don't know, I've been sick. I've been dying for some reason. But anyways, 2 axials is a big no-no because of diaxial interactions. I actually don't know if that would count as diaxial, but 2 axials is a big no-no. So that would actually be 5. The rest of the cyclohexanes only have 1 axial substituent, and they just have different sizes. So here we have an axial methyl, right? Here we have an axial ethyl, and then here we have an axial isopropyl. So as you can imagine, the smaller substituent would be the more stable one if it's on axial. So this would actually be my second one, this would be my third, and this would be my fourth, just because. So methyl's the smallest, ethyl is bigger than methyl, and then isopropyl is bigger than ethyl and methyl. So we would not want isopropyl on an axial position compared to the other two. Okay, so as an example here, I have cyclohexanes in its different conformations. So there are different conformations that you can fold a cyclohexane into. I'll actually go here on the side real quick. So if we think about the cyclohexane, it has different like folds it can do. And the most stable is the chair conformations. So you've been seeing actually up here, all of these were chair conformations in the first example. So that's the chair conformation. After that, sorry. After that, there's the twist boat, then the regular boat, and then there's the half chair, which is the least stable. So twist boat actually looks like this first example here. This is a twist boat. These middle two here are both boats. Okay, and we don't have any half chairs, but these last two are chairs. And then I will grab a sip of water. Okay, so right off the bat, we know our chairs are the most stable. So we can look at this, or these two. So I see I have an ethyl on an axial position here. And this is equatorial. On the right one, I have an equatorial ethyl, but I have an axial methyl. Right, so which one's more stable? So because ethyl is bigger than methyl, we would want the ethyl to be on an equatorial position. So this would actually be more stable, and then this would be the second most stable. So after that, after the chair, we have the twist boat, right? And we only have one twist boat here, so this will be number 3. And then we have 2 boat conformations of the cyclohexane in the middle. Here, this one has an axial ethyl. And this one has the equatorial ethyl. So once again, the ethyl should be on an equatorial position if it is possible. So this one is more stable on the right. And this one will be the 5th because the ethyl is on an axial position. And actually, this molecule, or this boat, also has a methyl on an axial position. So we have 2 axial substituents, which is really unstable. And that's it. That's it for today's video. That was cyclohexane stability. At the end here, these are the different conformations of cyclohexane. I didn't have a half chair example, Half chair would look like this. It kind of quite literally looks like a half chair. It's kind of weird. Don't take my drawing to be exact, but that's something like how a half chair would look like. But those are really unstable, so that's the most unstable conformation of the cyclohexane. Anyways, if you guys found this video helpful at all, make sure to subscribe. And I'll see you guys next video. Thanks for watching. Bye.